So today we will discuss about different numerical problems on risk analysis and vulnerability. So mainly we will see how different risk analysis methods can be utilized to find the amount of risk involved in a system. So let us see the first example. This example will show you the application of the Delphi method. Delphi is a very well-known risk analysis method by which what we do is we place some questions to a group of experts and we ask the expert to rate the questions or rate the let us say failures, and like for example here in a watershed we have observed three types of failure. Now one is lack of rainfall, another one is excessive erosion, and another one is conversion of land use. So all three of these is causing reduction of water holding capacity of the watershed. So this conversion of land use means forest land converted to agricultural land or agricultural land converted to urban land. So whatever is the amount of impervious area increases with the conversion of land use, because in case of forest there is no impervious area inside a forest, but when you convert that forest into agricultural land, which enables a large area of land to be exposed, there what happens is the amount of impervious area get increases, and then if you convert that agricultural land into urban land, so when an urban land is created due to the pavements, due to the cementing, what happens is no water is allowed to infiltrate on those land. So what happens is the water holding capacity of the watershed become reduced. And you see, when there is forest, due to the plants and their roots, the volumes of water is retained in the watershed. But when it is agriculture, the amount of root area get reduced. So the water retention capacity decreases. And when there is urban land, when we convert the land into urban land, suppose settlements or industry, then what happens is, as there is no scope of infiltration, the land becomes impervious, and as a result, water after falling, it just run off to the nearest channel. So as a result, there is the water holding capacity of a watershed get reduced, which ultimately will results in failure of watershed, because watershed is healthy when it can hold water, and it is unhealthy when it cannot hold water. Now, what happens is, as I have said, in case of Delphi method, we place these three failures to the expert. Suppose we have hired three experts, okay, and these three experts were asked to rate the failure as per their knowledge. That means which one is more significant failure compared to the other. Whether lack of rainfall is most significant, or excessive erosion is most significant, or conversion of land use is most significant. That the expert must rate with the help of a scale out of 100. So percentage means 100. Now, as you can see, this expert has rated lack of rainfall as the most significant because it has given 40 to lack of rainfall, 25 to conversion of land use, 12 to your excessive erosion. Now, note that all these ratings are made out of 100. It is not that this plus this is 100, but it is 40 out of 100, 12 out of 100, 25 out of 100, because 100 is the scale. Now this expert is 100, it read 24 to lack of rainfall, 40. He is confused between these two. He is saying that both of these two failure is same important. So equally important. So that is why he has given the highest numbers to both of these failure, and the second highest is lack of rainfall. In case of expert 3, he has given his own rating. Now, what we do is in a Delphi method, we just average these ratings. That means this plus this divided by 3. So this is 74 and 114. So this is 3. So what it is coming is, it is coming around 38. Now again you can do this, you again average this 40, 80, 92. So it is 92 out of 3. As there are 3 experts, I am dividing it by 3. If there are more n number of experts, you divide by n. So this becomes, how much it is becoming? Okay. So it is becoming around 30. It is coming around, you can say, it is coming around 30.66. 30.66. And this will come around, suppose 75 plus, I think it is more or less 20%. So 95 by 3. So it will become 31.66. So which one is highest? I think this one is highest compared to 30.66 and 31.66. 38 is highest. So this becomes your most significant failure as per the Delphi method. This is first, this is second, and this is third. As the average of these ratings for lack of rainfall is 38, for excessive erosion is 30.66, and the conversion of land use is 31.66. So if you compare all these 3 values, you can find that lack of rainfall is the most significant failure, as the average of ratings is highest for this lack of rainfall. Okay, so this is the way you identify the most significant failure with the help of Delphi method. So this example shows how you can identify the most significant failure with the help of failure mode and effect analysis, FMAE. Okay. Here also the same three failures are given: lack of rainfall, excessive erosion, and conversion of land use. Now here you see these are the three failures. Now what we do is we try to rate this failure with respect to its severity, occurrence, and detection. Severity signifies that if this failure occurs, right, then how severe can be the impact, right? For example, if there is no rainfall, the entire watershed will be drought prone. So, among these three failures, whose severity is higher? Now, here you can see with the help of these ratings, we can understand that the lack of rainfall has the highest severity, followed by conversion of land use and excessive erosion. Now let us see the occurrence. Now, what is the chance of occurrence of this failure? Which failure has the higher chance of occurrence? That means I am saying that this failure can occur, was observed in failure in the last 10 years. 10 years. However, how many times this has happened? This has occurred. So that chance of occurrence or frequency of occurrence of the failure is rated by this number. 10% means minimum occurrence, 40% means out of 100 times, 40 times this failure can occur. So this occurrence actually shows the chance of occurrence or frequency of occurrence of the failure. And the next is detection. Now detection signifies that how well this failure can be detected. Look, there are different types of failure. Some failures can be detected instantly, and some other failures can be detected after a very long time after their occurrence. For example, uh, if there is a conversion of land use, then in the initial year, you cannot detect much failure in the watershed. But after few years, you will see that there is a significant reduction in the water holding capacity of the watershed due to the change in the land use. So, as you can see that 10% means this type of failures is rarely detected, and 50% means this type of failure is very commonly detected, or I can say instantly detected. Okay. Now, how to find the most significant failure among these three failures? What we do is we simply multiply these three. 40 multiplied by 10 multiplied by 50. So it becomes, as you can see, and then there is three numbers, 20,000. Again, there you multiply all these three. So this will become your this is coming to 12 into 40 into, it is coming 19,200. And last is this one, 25, 40 and 10. So 25, 40 and 10. So this will be your This is coming up to 10,000. So according to the FME method, lack of rainfall is the number one significant failure, followed by excessive erosion, and lastly, conversion of land use. So by the help of FME method, we can identify the most significant failure by just multiplying the severity rating, occurrence rating, and detection rating of the failures, and then comparing the product of all these failures to identify the most significant failure. So this is another type of problem that can come under this risk analysis and also the adaptation and mitigation procedures. Here what you see is they are given the data of the discharges in cubic meter per second, and they are asking you to find the risk value for each of the discharges. Now risk value R is calculated by the probability of risk, right, multiply by the risk value. Now this risk value is either predetermined, predefined. If it is predefined, then just calculate the probability of risk and multiply the value with it. You will get the final risk value of the failure. And if it is not defined, then you have to first find the probability of risk. And if the data of risk value is given, like for example, here it is said 100 per cubic meter of discharge is the risk value. That is, for this amount of discharge, we have to waste, rather I would say, 100 rupees. So this 100 rupees, then suppose if I can find the probability of this discharge, then what will happen is the risk value or final risk value of the discharge of January will be the probability of the discharge multiplied by, as this is 50 cubic meter, then you will just multiply 50 into 100. So whatever the probability is multiplied by 50 into 100 will be your final risk value. Now how to calculate the probability? It is very easy. First, rank all the discharges in the descending order. That means the maximum discharge gets the highest rank and the minimum discharge gets the lowest rank. So here, as you can see, this is the highest discharge and followed by this second. This is the third, and here you see both are in the same value, 250 250, the discharge of June and the discharge of October. So they will be assigned the same rank, and then the next discharge, that is the 200, it will be assigned the rank of 6th, because we have a same discharge in which is 4th ranked discharge, but as two numbers or two discharges has the same rank, which is 4, that is why we have to begin the next rank as 6, because the rank and the number of data must be equal. That means here there is 12 number of data, so your rank must stop in 12. Okay, it cannot stop in 11, 9, or it cannot stop in 13, 14 also. So that is why when there is equal discharge or equal magnitude, give same rank, but assign the rank to the next discharge or next value by considering this double rank. So here, as there is fourth rank discharge, I am assigning the rank 6 to the next discharge as per magnitude. Then this is 6, and then this I will say 7, this is 8, 9th, then your 10th, then your 11th, then your 12th. And as how you can calculate the probability? Probability is the rank of the discharge divided by the total number of discharge available in your data set plus 1. So if this is 12, then you just add 1 to it. So let us take an example. This is your 12th number discharge, this 50. So this will come 12 by 30. So the probability of that discharge will be, let us calculate. So this will be 12. So it is 92% probability. So lesser the discharge, more common it will be. Less the rank, more common is the discharge. So 92, so this will be 0.9230 and then going on. So you just take the 3 digit after point. So we ignore all other digits. So let us see this with the probability comes to 923. This is the discharge value. Per unit of discharge, you have 100 rupees risk value. Multiply the 100. So this will become your this will become your 4,650. This will be your final risk value of this discharge, very minimum value. But if you calculate the risk value of this highest discharge, which has a rank 1, so what is its probability? 1 by 13. Then you see 1 divided by 13, it is coming only 0.076. 0769 it is coming, so you will take 0.077. Now you multiply 0.077 multiply by, this is 450, then into 100. So it is coming your way 0. So it is coming as so it is coming to as 3465. And similarly, what you will do is you will find this is your FRB, final risk value. So similarly, you will find the FRB of Jan, Feb, March, April, May, June, July, August, September, October, November, December, and then you will add all these FRBs. Right? Okay, so in the last problem, what we do is we calculate the final risk value of each month and we sum it to find the total risk value, which will show you the risk, actually the risk value of the watershed, okay, with respect to the discharge term, or we can say risk value in terms of discharge. Now, if I take this problem, this example 4 problem, this is the discharge data given. With the help of natural hazard based approach, you have to find the risk value. Here also, you will adopt the same method. First, rank it in the descending manner. This will be 1, and then this will be 2, this will be 3, both of these will be 4. So this will be 6, this will be 7, then 8. 9, 10, 11 and 12. The same data as the previous problem. After that, we'll find the probability of this data, 12 by 13, 11 by 13. This will come around 9 to 3. This will, I think, come how much? Let us calculate. I'm using the calculator. So this 11th rank discharge will have a probability of 0.846 and so on. Now, the natural hazard based approach, the formula for calculating risk with the help of natural hazard based approach is probability multiplied by the vulnerability. Here, vulnerability means the amount of discharge that will cause flood or the amount of discharge that may cause drought, or if the rainfall values are given, then the amount of rainfall that can cause flood, or the amount of rainfall that can indicate storms. So these things are vulnerability. Generally, vulnerability is a constant value, that is a level. So many times we use flood level or flood discharge as the vulnerability value. So if we take 450 as the flood level or flood discharge, so this vulnerability this will become 450. Generally, the highest value in a data set is assumed to be the vulnerability. And then what we do is we calculate the probability of all the values in the set. January, February, March, April, May, June, up to December. And then we try to multiply the probability with the vulnerability. Now, this will give, as you can see, that the probability of the minimum discharges, lower discharges, is higher compared to the probability of the higher discharges. So if we multiply the probability of this lower discharge, suppose this one, you see, and if vulnerability is assumed to be 450, what will happen? 0.923 multiplied by 450. So this will be let us find it from the calculator, 0.923 multiplied by 450. Now this will be our 415.35. And this is 0.846, which is higher discharge compared to the January discharge. February discharge is higher compared to the January discharge, has a rank of 11 compared to the 12, that is the rank of January. But you see, the probability is 0.846. So if we multiply 0.846 with 450, it will be 380. 380.70. So you see, if I consider this as the risk value, the lower amount of discharge will have a higher risk value compared to the higher amount of discharge, because this is higher. This is higher because this is 11th rank discharge and this is 12th rank discharge. So 12th rank discharge will have a higher risk value compared to the 11th rank discharge, which is not true, which doesn't indicate the exact picture, the real picture. So that is why what we do is, instead of using the probability, we use the inverse value of the probability. So that means we use the return period of the probability. So if we inverse it, again if we take the what is the return period of this January discharge? Let us calculate 0. Sorry. So it will be 1 divided by 0.923. It is 1.083. And what is your the return period of 11th number discharge? That means the February discharge. It is 1 divided by 0.846. So it is 1.82. Sorry, 1.182. So here you see return period of January discharge is lower compared to the February discharge. That is okay. So if I to find the risk value, if I multiply the return period, which is indicated by T, with the vulnerability, then we will get the risk value, which will represent the correct risk of the discharges. Because when we multiply 1.08 with the vulnerability 450, and when we multiply 1.18 with the vulnerability 450, this value will be lesser to this value, which is the correct, which is actually the correct picture. So this will be your, if I multiply 1.18 multiplied by 450, this is coming as 531, right? And if we multiply 1.08 with 450, so this is coming 486. So naturally 486 is lesser to 531. So the risk value of the last rank discharge is lesser compared to the 11th rank discharge. So this is the correct picture. So in same way, you have to calculate the risk value of each of the discharge by multiplying the return period of the discharge with the vulnerability, which is assumed to be the highest value in the data set. Here the highest value is 450. So we multiply the return period of each of the discharge with the 450. And what is return period? It is 1 by P. So this is the way, and your answer should show the risk values of all your discharge. And if the vulnerable value is not mentioned separately, always assume that the highest value among the data set will be the vulnerability. So if 450 is the highest value in this data set having 12 discharges, then 450 will be the vulnerability. And if your suppose 340 is the highest value, then 340 will become the vulnerability. This you must assume if nothing is said about the vulnerability. So this is your natural hazard based approach. So let us begin. Here the earlier example ask you to find the risk value or the risk with the help of natural hazard based approach. So the how we have calculated is, let us find it. So risk value R is equals to, actually the formula is like this, probability into vulnerability. But when you really calculate it, you try to multiply the return period, multiply the vulnerability, and always assume the highest value as the vulnerability if no other value is mentioned, right? But the vulnerability based approach is something different. Here vulnerability approach is the risk is equals to exceedance probability of the discharges or will fall or any event. What is the probability that the value of discharge will exceed the vulnerable discharge? That means if flood level or if flood discharge is 400, then what is the probability that this discharge will exceed the vulnerable discharge of 400? Here you see only how many value is there? Only one value is there which is exceeding the probability or vulnerable value of discharge, that is 400, assumed to be 400. Now how to calculate the vulnerability based approach is the same way. What we do is here the vulnerability or the level of vulnerability will be mentioned like 400, right? After that what you will do is you will just find which are the values that is exceeding this vulnerable value. Suppose this is 400, here only one value is exceeding. So what you will do is you will find the probability of each discharge. That is, this will be 1, this will be 2, 2, 2. So this is 4, this is 5, this is 6, this is 7, 8, 9, 10. And you find the probability 12 by 13, 11 by 13 and so on. Here you see the value 550 is exceeding the vulnerable value of 400. What is the probability of this 550? It is 1 by 13, and 1 by 13 is 1 by 30. It is 0.076. This is the vulnerability, right? This is the this is the probability. Now, as I said, you have to find this formula of finding risk is actually it is better to calculate the return period than to calculate the probability. So, but here, as you have to there is no requirement of multiplying the probability with the vulnerability. So you can straight away take the probability of this and then you just find the return period of this probability, right? Right. So the return period will be 1 divided by 0.076. It is coming up to 13.157. 13.157. So this is your return period of this probability. If more than one value is exceeding, suppose this is instead of 400, this is 300, then you have to show the return period of 310, 340 and 550. So this way you have to calculate the return period and you have to show it in your answer. And as you can see, if we consider the return period, the risk of the highest discharge and the risk of the lowest discharge will be reflected in your risk value. But if you give the probability that that risk will show the opposite of the real picture. So always remember, a higher discharge or higher rainfall will always have a lower probability, but its return period will be higher, and so will be its risk. It is a common sense. Again, lower discharge will have a higher probability, but will have a lower return period, right? And will have a lower risk, right? So this is the common sense, or this is the normal logic. So always use the return period instead of probability while calculating the risk value of discharges, rainfalls, etc. Okay, so